running a couple sections together here. I think it's going to be better this way. We'll find out. So zeros of a polynomial, the fundamental theorem of algebra. So getting into what in the world we do with these polynomials. So a reminder, the zero of a polynomial is a value of x that makes the function equal 0. And so it's often an x-intercept, though if it's not a real number, it won't be an x-intercept. And what we want to focus on first is how many zeros a polynomial will have. It's going to have as many zeros as the degree of the polynomial, as long as you count multiplicities and you count any non-real or imaginary zeros. So multiplicities are what we get when a zero, or a factor x subtract c, shows up more than once. Let's look at a problem here. So looking at p of x here, x cubed subtract 3x subtract 2. If it's factored down, it's x subtract 2, x plus 1, and another x plus 1. So we wrote it with a square. So looking at it this way, this is a third degree polynomial. If we count the x subtract 1 zero twice, because it comes from a factor that shows up twice, then we have 3 zeros for the polynomial, and it's a third degree polynomial. And then just a reminder, the way we get a clue, which will help us solve the problem, that a particular factor zero is going to show up twice and have that multiplicity within a polynomial is looking at the graph. If the graph touches but doesn't pass through, then it often has a multiplicity of 2. Whereas if it passes through, it's usually a multiplicity of 1, though it could have a multiplicity of 3 or a multiplicity of 5, any odd multiplicity. Most of the time it's either a multiplicity of 1 or a multiplicity of 2. Okay. So we're spending a lot of time trying to find these zeros, and whenever we've got a zero, we've got a factor. Graphing calculators are made of a lot of the techniques we used to use obsolete, so there's certain things I usually skip over, so I ignore the upper and lower bound rules and the Descartes rule of signs that are in the book. But one that I do find handy is the rational zero theorem, and this is one of those theorems that the definition really isn't a whole lot of help, so we'll get to an example. But what I want you to focus on with the rational zero theorem here is we're going to be using the leading coefficient, and we're going to be using the constant to find these possible rational zeros. And this only works as long as we've got integer coefficients, so they're nice whole numbers. Okay, so the way this works is we go to the constant, so in this case -9, and we list all the possible factors of -9, the numbers that divide evenly into -9. So those would be 1, 3, and 9, and also -1, -3, and -9. And then we look at the leading coefficient, which is a 2 in our case, and all the factors of 2 are +1, +2, -1, -2. And then we're going to look at all the ratios of the factors of the constant divided by the factors of the leading coefficient. So just be systematic. So what I like to do is take the first factor here of my constant and then put it over all the possible factors of the leading coefficient. So 1 over 1 and 1 over 2. 1 over 1, 1 over 2. Then I take the next term in my factors of constants, which is a 3, and put it over all the possible factors of the leading coefficient. So 3 over 1, 3 over 2. Then I take the 9, 9 over 1, 9 over 2. And then I cleaned it up. And then I put a plus or minus in front just so I don't have to list them out twice. I'm lazy. You haven't noticed that yet. And this is our list of possible rational zeros. So what we've got here is a list of 12 different possible rational zeros. We've got a third degree polynomial, so we know there's only a total of 3 actual zeros for this polynomial. So there's a lot of extras. And again, this is just kind of a tool that helps us interpret what we see on our calculator. You'll see in a minute. I promise. Okay, so graphing it on a calculator, our third degree polynomial, we've got 3 x-intercepts, so those will be our 3 zeros. Any rational zero p of x is going to be on our list, but the list also includes many values that are not actual zeros of the function. And we'll come back to this later. If it has an irrational zero, it's not going to be on the list. So getting back to our list and looking at our graph, it looks like +1, -1, and -9 halves, right here between -4 and -5, look like x-intercepts, and they're all on our list. So to verify whether or not these are actually zeros of our polynomial, we could plug them into the function, but that's tedious. What works much more quickly is a synthetic division. So getting in here is our polynomial. These were our zeros that look promising, both from our list of possible rational zeros and on our graph. So to prove that they actually are zeros, we start with the synthetic division. So arbitrarily, I took the 1 first, divided it synthetically, and got a remainder of 0. So that tells me P of 1 is a 0. So x subtract 1 is a 0, and x equal 1 is a 0, and x subtract 1 is a factor. And then I can keep going. Negative 1 looked good, so I'll take the negative 1, divide it into what we've got left, this quadratic, do the synthetic division, and again we get a remainder of 0. So P of negative 1 is also a 0. X equaled negative 1 is a 0, x plus 1 is a factor. Then taking the negative 9/2, dividing that in, again I got a remainder of 0, so I know I have a 0. So our polynomial factors down to x subtract 1, x plus 1, x plus 9/2, and we're fully factored. The 2 here is my leading coefficient here, the 2, and what that does is clean up the fraction here, so that when I multiply this all back together, it would multiply and simplify to be what we started with. And then the zeros of the polynomial are the 1, negative 9/2. We had a third degree polynomial, so we've got 3 zeros and 3 factors. Okay, I'm going to need a few more examples. This one's a little messier, especially with that constant there of negative 78. When we list all the possible rational zeros, it's a very long list. So you don't always want to bother making the list of possible rational zeros. It's a nice tool. It helps us interpret what we're seeing on our graphing calculator. For example, looking at the graph here, I can see there's a 0 somewhere between 0 and 1. And of my possible rational zeros, 1/2 was the only fraction that was between 0 and 1. So 1/2 looks likely. Versus, and there's lots of other fractions, 1/3, 1/4, and we could zoom in on our calculator, but this is much faster. So on the calculator, it looks like -3 and some fraction between 0 and 1 are zeros of the polynomial, and those are on our list and look promising. So using the synthetic division, the -3 worked, the 1/2 worked, and what we're left with here is a quadratic. So then we can take the quadratic, use our quadratic formula to find our 2 remaining zeros. Because right now we've only got 2 zeros. We started with the 4th degree polynomial, so we know there should be 4 zeros. So going through using the quadratic formula, this cleaned up nicely, and what we got for our zeros here are a couple of imaginary numbers, 1 plus 5i, 1 subtract 5i. Because these are not real numbers, that's why they weren't showing up on the graph. The graph is a graph on a real number line. Non-real numbers won't show up on the graph. So what we started with was our polynomial. It's a 4th degree polynomial. We have 4 zeros, the -3, the 1/2, 1 plus 5i, 1 subtract 5i, and then we've got 4 factors, the x plus 3, x subtract 1/2, x subtract 1 subtract 5i, x subtract 1 plus 5i, and then our leading coefficient of 2, which cleans up our fraction. 4th degree, 4 zeros, 4 linear factors.